Uh, the future, what we're going to lay out, we're going to begin today talking about clustering. Clustering and classification are pretty similar in a lot of ways. And we will go through one algorithm today. It's a fairly straightforward, simple algorithm, and depending on time at the end of class, we'll also go into Weka to show not just how to use the k-means algorithm, but how you can start visualizing your data. But before we begin, questions? Nick? I take that as a
Gucci.
As a no?
Gucci video.
Okay, so
Curveball.
is it going to begin? I didn't begin my session.
Turn on their mic so they can ask questions.
And when it goes full screen,
It turns off their mic.
it turns off their mic. Right.
And say, do you want to give them
So, today we're going to talk about clustering and what the general problem is here. Pardon? Okay. So, clustering is essentially a similar idea in some ways as classification, except with one main difference. We're not predicting a class. Okay? All we're doing is we're going to be seeing different groups of your data instances grouped together by some measure of similarity or dissimilarity. So that groups are going to be grouped based on their attributes. Those in each group are going to be more similar, whereas objects between groups will be less similar. And that's the basic idea.
Objects between groups, what do you mean by that?
Well, if you have an object in, say, group A,
Okay.
and an object, so group A is going to consist of items that are in some way similar to each other.
Okay.
And that's going to depend upon your similarity measure and what attributes you're measuring.
Okay.
Objects B, or cluster B, this is the idea, will consist of other objects that are also similar to each other, but A and B might be different. So a real world example, I was going to do this with some pictures later on, but would be in terms of, I was doing this example with Drew just before class, a cat and a dog versus a ballpoint pen and a pencil. Okay? You could argue that a ballpoint pen and pencil are similar. A cat and a dog are both mammals. They both have 4 legs, 2 eyes, tail, a head, nose, ears.
Heart.
But it's covered in that.
Right, that's covered in mammal. Okay, so one could argue cat and dog are similar to each other. They're not exactly the same object.
What about cat dog?
And a pen and pencil are more similar to each other, but there's not much similarity between,
Pen and a cat.
right, a pen and a cat.
Okay.
So that would be an example. You're going to cluster your writing instruments. You'll cluster your pets or mammals.
But then you could do it by color.
You could, okay, good observation. You could also cluster in different ways. And you're going to be, so a lot of that is going to hinge on your similarity measure, and also what attributes you're going to be looking at or weighting if you're weighting at some attributes more than others. Okay, so there's different ways, there's sometimes different clusterings, and it's not always, use a cliche, cut and dry that way.
So,
So-
our similarity measures you're talking about, that's from our association?
No, those are the measures we talked about a long time ago towards the beginning.
Right.
So you can look at distance measures, distance in space. So there's another clustering. You can look at galaxies. You can think of as clusters. And then you can have hierarchical clustering. So you can have clusters of clusters. Okay.
Okay.
So that what they're a good measure would be the distances involved.
Okay. So it's not about the association?
Well, I mean, again, and so if you're looking at, so in some of the work I do, you've got the hypergraph and you've got attributes of, you can start thinking about your mammals and what are the characteristics or attributes of these and what are their similarities and how are you going to measure similarities? Well, there's different ways to do that.
Right.
But that's, you can do set intersections and unions. How often do they have properties in common? Like what we talked about.
Okay.
So you could use different, whether it's a Hamming metric, which we talked about for binary zeros and ones, whether it has certain attributes.
Okay.
So that's going to depend upon the
Right.
context of your problem.
I remember that.
You remember that now?
Yeah.
So you can think of, and the reason I say that clustering, and there are a couple of reasons I say clustering and classification actually could work together quite well. One of them is you can think of clustering as unsupervised classification. That is, you're trying to classify these objects into different groups, but you're not trying to determine just a particular class. Some set of attributes determining a class. For using the weather example, if you remember that one, where you took the inputs of your weather conditions and outlook to determine whether you were going to play or not. Okay? But instead of that, you're just saying, okay, what are the characteristics? Here are all the attributes. Here are all the features. What's common with these particular weather conditions versus these particular weather conditions? Do they cluster naturally? Does that help? So one way you can think of it is it's unsupervised. You're not trying to get a particular class out. You're just trying to, and it's really useful. Another way that I, in my own work, use clustering, because you don't really know what class you might be interested in. I mean, that's part of the problem. But what does the data look like? And it often helps you see, aha, there's this group over here and there's a whole nother group over here. And how can we use that to our advantage? So, part of the difficulty is what constitutes a cluster, right? And the answer is not always clear. This is a slide from your text. But basically here you've got original points in part A here. You've got a whole bunch of different individual points. They've been graphed in 2 dimensions. And as humans, you can start identifying different clusters, right? You could think of this, well, you've got, I can draw on here, can I?
Yeah. Click the pen above one. There.
So here,
There you go. Click on, no. Go that, there. You can actually touch your smart because it's working.
So it looks like there's a cluster there and a cluster here, right? And that's what you see in part B, is you see you've got these two clusters. But that's if you divide it into two clusters, but notice in part C, they've actually divided it into 4 clusters. We've got this large cluster, kind of oblong one here, and then we've got this smaller one down here, and then another oblong one, big oblong one down here, and then the 4th one here. Or maybe you could identify it as 6 separate clusters. That oblong one splits into 2. Yeah. Don't laugh at the,
One point feels left out, I guess.
It's okay. At least they're all circles. Oh, nope. Messed it up now.
okay? So you can think of it as 6. So what is a cluster? And as I say, in humans, we kind of identify that you could, and there are different ways of clustering. One of them will say, okay, look, you can break this 2, and then you can further break that into 4, and then further break it into 6.
So in your pencil pen, so to speak, like you can have your original points as writing utensils.
Right.
And 2 points would be like pen, pencil, and then for like you can break down pens and do black and colors. And then
You could do that, right.
Okay.
Depending upon what level of detail you're interested in, what algorithm you're going to use. So, I mean, ultimately, you know, it would be pointless. You could start breaking down the students here into, that we have 9 students in the room, into clusters of size 1, 9 clusters. Well, now there's not really a cluster.
Right, yeah, so
Right.
what is the definition of a cluster?
Well, it's just a
You kinda
simplified.
do
It's a
Yeah.
simplified thing, right. I mean, that's the thing. It's an organizational, basic organizational principle. And ultimately, it's kind of like in statistics, you summarize groups, but ultimately everything is an individual object. I mean, if you start talking about the population of the United States, you've got so much data that it helps to start summarizing it for our own informational processing. Because I don't want to start thinking about 330 or however million different individuals there are in this country as individual objects. I can't do that. It's just too big of a problem, right? So instead you break it down, okay, so many, you can break it down male, female,
People by state.
Gender,
by state, by gender,
race.
by adult, by age, and so on. By income levels and I mean, there are many different ways to cut it down. This is another example. I don't know how well it shows up here. The idea here is, this was the best I could find right away. I was trying to look at, this is more text classification. So you can start using this as clusters. As I said, I use classification. Well, it's a clustering of different texts and their similarities from one text to another. You could use this with email, okay? So you have spam filters on your email. How does it detect spam versus messages?
I looked that up, and I guess Bayesian.net was one of the things that they used.
Right. And there are many different algorithms. But and then again, the distinction here is, do you have clusters? Do you have a certain type of email and another type of email? Different types, and automatically cluster them according to what they have in common. So. in that example, spam, you might be searching strictly for spam and classifying something as a spam. But in clustering, you're just trying to separate one type of email from another type of email without knowing what the two types necessarily are, seeing what the groups are. So the basic types of clustering that we've actually kind of already discussed, it breaks down into two big groups. You've got hierarchical clustering, which is where you start having clusters of subclusters. Like we saw before, you can start breaking it down. You've got big clusters, and each of those clusters have subclusters. And there's even here, there's two essential concepts here. One is a bottom-up approach, where you're going to start with small clusters and then combine small clusters together to create super clusters from the small clusters. So that's what's called a bottom-up approach, or you can do the top-down approach. You start with big clusters, you divide the big clusters into smaller clusters.
Which one of those would prove better, per se? Like, to get more accurate clusters, what would you?
It's going to largely, they each have strengths and weaknesses. It helps. These are the approaches to the different algorithms, and I don't have a perfect answer for you on that.
So it's just situation then?
Right, and you try sometimes. I mean, with a new data set, you don't always know what's going to work best.
Well, yeah, it depends on the data that you.
You noticed
Right.
even on that Weka experiment for quiz 1, right? Sometimes one algorithm did better than another one on one data set, but on another data set, the reverse might be true. And so you don't always know ahead of time which is going to work best.
Okay, so here's the way I'm thinking about it, like, if you get a lot of data for like census data or something.
Right.
You have a bunch of information that's not really split up into anything, so you just have this huge group just right in front of you. So you're gonna use the top-down thing, right? So you split your large group into like different clusters that are similar.
That would be a top-down approach,
Right.
right?
So like, if you have a bunch of information from, I guess, sales information you can do. So like you have a bunch of sales for one product over here, over here, over here. You have a bunch of data for a bunch of different product, and you have like a bunch of small data sets. And then you have to see how those are similar, and then you go bottom up, right? So the stuff that's
I
similar.
can see what you're saying there. So like,
Right.
you know, there's 10 stores in a region.
Yeah.
So why is it these 10 stores? You know, these stores are related. Their sales are really strong for a certain product versus another one in this region. But in another region, some other product might be the hot
Yeah, so like,
commodity.
depending on how you want to cluster it, you can do like total sales of each product throughout every store, or because
Right.
each store is going to have its own.
Right,
data
and
set.
then it's products and then regional.
And it's also going to depend upon what you visualize, what attributes you're comparing to each other. These are when I'm talking about this, I'm talking as much as anything about the algorithms that are developed for these. There are too many and that was one of the things people brought up. There are a lot of algorithms out there, a lot. And there's a competition to get better and better algorithms all the time. My point being that some of these work on a bottom-up principle and some of them work on a top-down principle. Sometimes one will work better than another, and I can't. tell you, in fact, we're gonna go through hopefully k-means today. It's very simple. So here are some common algorithms. We're not gonna go through all of these. Okay? I'm gonna say that out front. Okay? But they're great way, I'm gonna talk about 4 different categories and just briefly, again, describe, these are different ways of approaching the clustering problem. So you've got what are called partitional. I think did we talk, I missed a slide because hierarchical. This goes back and forth. I must have missed that slide. So versus hierarchical, you've got what are called partitional algorithms, which basically just separate out your clusters. It's not a hierarchy, it's just saying, here's 4 distinct clusters. They're non-overlapping, mutually exclusive, for those who've seen that term in probability and statistics. Okay, so in other words, they're separated. You've got a cluster and a cluster. And nothing overlaps between them. I mean, they may appear overlapping, but they're not the same. So a good examples of partitional algorithms are k-means, which is a very simple and effective algorithm, which we'll talk about. K-medoids is just a slight variation of that, which we won't talk about, but it's really the same idea. We've got density-based algorithms, how dense areas are. And a couple of those are called density-based scan and SNN, which the only difference between those two is you're going to be your measure of similarity.
So would the density base be like a population type of thing?
Right, so you're going to distinguish clusters, densely populated clusters by regions of less dense things. So if you think of population centers would be a great example, you can start clustering cities that way.
So is this kind of like what the Division of Wildlife does to like guess how many fish are like in each river or something like that?
That would be more just statistics. There's a particular method that they use for that. So k-means. So Eric, you used k-means clustering before. So the basic idea, and here's the basic code here, is you're going to choose some number of clusters. We call it K. K and k-means. So you can say, okay, we want 5 clusters. We want to break this data up into 5 distinct pieces. And the basic idea is we're going to just initialize k centroids. So in your box, you're going to start with just what we're going to start with 5 points that are going to be your centers. And then what you're going to do is, there's a loop here. We're going to form our clusters by going through each of our data objects, each of our instances, and measuring, using our measure of similarity, the distance to each of the centroids. And the centroids that's closest to that particular instance is where that instance is assigned to that centroid. So it's basically going to the closest centroid. And that becomes the cluster around that centroid. And then you recalculate all your centroids. Centroids being just your center of mass, your centers. You're just going to recalculate them until you reach convergence. Your centroids don't move, they begin being stationary. Very simple code. It has its time complexity, depends on the number of points, the number of clusters, the number of iterations, the number of attributes. Space complexity, that's not necessary at this point. The upshot,
So this can get pretty complex pretty fast.
yes, and I'm gonna go through advantages and disadvantages, okay? Big advantages, simple, effective. It's conceptually very simple. It's very simple to implement, it's very simple to run, it has a single parameter K. The number of clusters.
Yeah, but wouldn't you also have to input your data set?
You have to input your data sets, yeah. You're gonna have to do that with any algorithm, otherwise you can't run your algorithm. Okay?
Well, I'm just thinking, that.
Right, but I mean, to run
There's
it,
not.
the only really thing you need to adjust is how many clusters are we gonna determine? Other algorithms tend to be much more complicated, may require more parameters to run, more parameters to tune and set, more complex. They can take many orders of magnitude longer to run. K-means is relatively quick. I like to think of K-means as quick and dirty clustering. It's easy.
Quick and dirty.
So one of the things about it is they may not generate the best quality clusters,
Okay.
but oftentimes you don't really need high quality clusters. Sometimes you're looking at clustering to guide you in more general classification.
So could you use clustering as a means of getting rid of some data that you don't necessarily need?
Could be. You could.
I see this more like looking at, say, video game metrics. You would cluster weapons or something and be like, okay, we should focus on these, not,
Not those. Yeah, you could do that, exactly.
or map types or something.
And there are ways around, I think for some reason,
It likes to skip slides.
it likes to
once in a
skip
while.
slides.
I like to skip slides.
There was the disadvantages after the advantages, and
So the,
Okay with disadvantage.
back to the time complexity thing.
advantages,
We had the number of points, number of clusters, number of iterations, and number of attributes.
right.
The iterations, is that how many times you want to,
How many times it's gonna run
okay.
through the loop.
So,
I don't know what happened to
the
that.
number of
There it
iterations
is.
will give you a more precise cluster.
So we'll finish this and go through Weka
Okay.
implementation of this on Friday. Is that, I didn't mean to cut you
It's
short.
okay. It's okay.
I found the slide that wouldn't appear. So, but, the class is
Yeah.
over, so, yeah.
What does it mean by a bad choice for K? I mean, a value too low or a value too high?
Either way.
Yeah, either way, you're right. I mean, an example, let me, bring the other class in.
When I did my K-star
An example
Too high or too low?
of too high would be 9 clusters for 9 people. But then now what are you clustering? We'll talk about that when we get into Weka and you can start seeing some of the visualization and how that can help us, guide us through that.
No, I was going to take it back to
Does that
when they're showing us the
help there?
Clustering.
I think